I tried to make the CAPS logo, and it's way too sharp. Like at the content where you can't like actually see it. And at first I didn't realize that. Actually, once I don't know why they stopped. That I actually wanted to pages on where it's like actually create a video. Yeah, to be able to like actually put it on and it shows that's what's on there. Cut it. It's really sharp. Yeah, so I tried to like I got
Okay, good morning everyone. Good morning. We started looking at Kirchhoff's laws last class. For radiation. Here is a brief summary. Okay. All right. The first statement is always true, and this is called as the unrestricted form of Kirchhoff's law. This is alpha lambda theta, function of lambda, and then the directions. This is equal to epsilon lambda theta phi. This is always true, regardless of whether thermal equilibrium has been attained. Okay. This is a surface property. Second thing, we can say that epsilon lambda, which is the spectral emissivity, is equal to the spectral absorptivity under the following conditions. Epsilon lambda is equal to alpha lambda if one or the other condition is satisfied. A, surface is diffuse, which means that epsilon lambda theta and alpha lambda theta are independent of direction. Or independent or not dependent on direction. Or we have the second condition. The irradiation is diffuse. Which implies that the surrounding acts as an ideal body. But it is not necessary that the temperature of the surrounding be the same as that of the surface. But thermodynamic equilibrium is not satisfied. Third condition under which this alpha lambda is equal to epsilon lambda is if everything is in thermodynamic equilibrium, which is kind of a no-brainer. So or C thermodynamic equilibrium, and the surrounding is an ideal body. Third one, alpha is equal to epsilon. first one. The surface is diffuse. Which implies alpha lambda is equal to epsilon lambda. And it's always true that the first one holds true. And then the surface is gray. Which implies that alpha, lambda, and epsilon lambda are independent of lambda. That's one situation. Second situation, or the irradiation is diffuse and the surface is gray. Which implies that alpha lambda is equal to epsilon lambda, as you can see from there, and the surface is gray. Or the third situation, which is again the same as this situation here, there is thermodynamic equilibrium and the surrounding is acting as an ideal body at the same temperature as the surface. Okay? The third situation, or equilibrium and surrounding is an ideal body. This is a brief summary of Kirchhoff's laws. And I want to make a note that typically we can recreate the presence of an ideal body by considering the surroundings to be very large in terms of a large cavity. Okay? So we can, ideal body typically is approximated by considering a large cavity, or typically we just call it as surroundings because we are interested only in surface transfer of radiation energy, so we are not looking at things taking place within the volume of the surface. So it's sufficient if my surroundings are some kind of a hemisphere, my surface is sitting here, that is still considered to be an ideal body. Okay? Large cavity or large surroundings. So when you see either the word large cavity or large surrounding, it implies that the surrounding is approximated as an ideal body. It will not be implicitly mentioned in the problem. Yes?
So you know body like the same as like a black painted body?
It's yes. You can have a body painted with lamp black or carbon black, and that can act as an ideal body. Absolutely, absolutely. Which is why it has a name black body. So in a textbook, they call it a black body. Okay. Now I'm going to solve a problem, and then after this we will start looking at radiation exchange between surfaces, which is where real problems start. We will start looking at how to model radiation in furnaces, and to cap it all off, it's of course not winter anymore, but I would like to take an example of an ice hockey arena and look at the kind of radiative heat transfer that takes place in there. Okay, and the different modes all coming together. So this is going to take place later down next week. So I'll spend 4 more lectures on radiation after today, and then we'll move on to convection. Okay? And in convection, my plan is mostly to talk about external flow, and then we will look into heat exchangers. Okay, so problem. So So we have a small body with a large surrounding in the following situation. So this is T is 1200 Kelvin. Typically, if you're not given it in Kelvin, you convert it into Kelvin because you're doing radiation heat transfer. It's surrounded by a large body, large surrounding. This is at 2400 Kelvin. You are told that the surface of the object is diffuse. The surrounding is large. And you're told that the spectral absorptivity of the object is given as follows. For object, this is the object. Alpha lambda versus lambda is the following plot. It's 0.1 from 0 to 2 micrometers. And it is going to be 0.8 after 2 micrometers. So this is 0.1, 0.8. Obviously, these are approximate results. If you look at experimental results, it will just be all over the place. Okay, there is not going to be any kind of a sharp departure from 0.1. There is no discontinuity there. Everything is continuous because radiation is treated as broadband. Broadband meaning continuous with wavelength. But for the sake of solving problems, we look at it as a discontinuity. So this is given to us, things that we need to find. The net radiative heat flux for the surface, for the object, and sketch the spectral emissive power of the object as a function of lambda. Which is E lambda as a function of lambda. This is very similar to one of your homework problems which I posted a couple of days back. Okay. So, how to tackle this problem is by first of all looking at the information given. Surrounding is large, which means that this is going to act as an ideal body. That's the first thing. Which means that its intensity is given by the Planck distribution, so we can make use of those tables that we already have for some of your homework problems. Okay, and I have posted, if you look at your Parliament page, I have posted the entire formula sheet for this coming exam, which includes the tables from I think 0 micrometer Kelvin all the way to 100,000 micrometer Kelvin. A couple of pages of numbers. So those encompass pretty much all the numbers that we need for this particular course and for the rest of your life. The surface is told to be diffuse. If the surface is diffuse, then we directly make use of Kirchhoff's law and say that, okay, if the surface is diffuse, epsilon lambda is equal to alpha lambda. So even if epsilon lambda is not given, I can make use of the same distribution. Okay? So solution. Surface is diffuse, so alpha lambda is equal to epsilon lambda. Obviously the surface is not gray because alpha lambda is a function of lambda, and so we cannot assume that alpha is equal to epsilon. Okay, but alpha is not equal to epsilon. And we also see that thermodynamic equilibrium is not maintained, surrounding is double the temperature of the surface. So we start off by making use of alpha is equal to lambda epsilon, alpha lambda is equal to epsilon lambda, and then use that to calculate the emissivity, use the fact that the surrounding is an ideal body at a particular temperature to calculate the absorptivity, and then calculate the net radiative flux. So let's do this step by step. I'm going to start off with emissivity calculations. So epsilon lambda is equal to alpha lambda, which is 0.1. And 0.8. We go back to the definition of emissivity. Epsilon. Typically, epsilon is a function of temperature. It's a strong function of temperature. So I would specifically write this as epsilon as a function of temperature. By definition, this is the formula. 0 to infinity, 0 to 2 pi, 0 to pi by 2, lambda comma e, sin theta, cos theta, d theta d phi. I have lambda comma b. So d lambda here, cos theta. Right, this is a standard expression that we've used multiple times. And we right away have to recognize that the integrals that contain the directions, if I look at them, this boxed integral and this boxed integral represents the spectral emissive flux or the spectral emissive power. Okay, so this I can rewrite as 0 to infinity e of lambda d lambda by 0 to infinity lambda comma b d lambda. Both of them being functions of wavelength and also functions of temperature. So that's the integral here. And likewise on the top. And by definition of epsilon lambda, we have the following. And you'll see that these problems are very similar to what we've done in the past. The only difference is that we now make use of Kirchhoff's law to say that, okay, if alpha is given, then epsilon is known to us. Other than that, this is pretty much same repetitive stuff. Epsilon lambda by definition is E lambda by lambda comma b. And so I'm just going to substitute for E lambda in terms of epsilon lambda, so cross multiply, substitute, and we end up with the following. So epsilon t, integral 0 to infinity, epsilon lambda, lambda comma b, e of lambda comma b d lambda. Which I'm now going to break into two pieces. Integral from 0 to 2 micrometers and then from 2 to infinity. Okay? So this is going to be 0 to 2 micrometers. The value of epsilon lambda at that interval is 0.1, so I'm going to do the substitution. So this is 0.1 e lambda comma b d lambda by 0 to infinity e lambda comma b d lambda, and then the remaining one is epsilon lambda at the range after 2 micrometers is 0.8 all the way to infinity, and so 0.8, this is from 2 to infinity. In the exam, I would not waste my time writing these steps if I directly recognize that, okay, this is 0.1 times the fraction from 0 to 2, this is 0.8 times the fraction from 2 to 8. So the first one is f from 0 to 2. So this is 0.1. It is very important to specify the temperature here. Okay, so I typically write it as at 1200 Kelvin plus 0.8 times f from 2 to infinity. Kelvin. This is the temperature of the object. Okay. F from 2 to infinity is rewritten as the following. So this is 0.1, 0 to 2, plus 0.8 times f from 0 to infinity, minus 0 to 2. Fraction from 0 to infinity is 1. So, is 0.1 plus 0.8 times the 1 minus I'll write the step for this particular part. For alpha lambda, I'll skip the details. How to calculate f 0 to 2. You first calculate the product of lambda and t. Lambda is now 2 micrometers. Is 2 micrometers times 1200 Kelvin. This is 2400 micrometer Kelvin, and then you take a look at the tables that are posted under your formula sheet. A portion of the tables are also available under homework 7, I believe. And f 0 to 2 that gives you the following number: 0.1403. Substitute, solve for epsilon t ends up being the following: 0.702. Does this make sense to everybody? Exact same procedure for alpha lambda. And why is it the exact same thing? Is because you have already recognized that the surrounding is an ideal body at the temperature of 2400 Kelvin. So all these calculations are going to be repeated for alpha lambda, but at a different temperature. So the fractions are going to be different, but the procedure is going to be the same. Okay. So we go back to the definition of alpha. So alpha is a very, very weak dependence on temperature typically. Okay. But by definition, this is 0 to infinity, 0 to 2 pi, 0 to pi by 2, lambda comma I absorbed, lambda theta phi, sin theta, cos theta, d theta, d phi, d lambda, divided by its counterpart without the absorbed portion. This is 0 to infinity, 0 to 2 pi, pi by 2, lambda comma little I meaning that this is incident radiation coming from the surroundings, sin theta, cos theta, all of those things. Sin theta, cos theta, d theta, d phi, d lambda. And please let me know if my writing is small for people on the back and the sides. Okay, can you all see my writing? I do the exact same thing as we did for the previous problem. I isolate the quantity with the angles, because that's going to be my spectral absorptivity, spectral irradiation, I'm sorry. Once again, I have the quantity within the brackets. So I'm going to write the first one as the following. So alpha is integral 0 to infinity. 0 to 2 pi, 0 to pi by 2 is g lambda comma absorbed. G lambda by 0 to infinity g lambda d lambda. Okay. That is that quantity, and likewise its counterpart in the denominator. Then we recognize, and of course alpha lambda by definition is g lambda absorbed by g lambda. So I'm going to substitute for alpha lambda instead of g lambda comma absorbed, so that alpha is integral 0 to infinity alpha lambda g lambda d lambda by g lambda d lambda. Then we recognize that this is an ideal body because it's treated as a large surrounding. So rather than write it as G lambda, I'm going to write it as E lambda comma B, but at a temperature of 2400. Okay, so this is now identical to alpha lambda E lambda comma B at 2400, because that is the temperature of the surroundings. And likewise this is 0 to infinity E lambda comma B lambda comma 2400 Kelvin d lambda. Makes sense to everybody? Any questions, please? The rest of the procedure is the same. I'm just going to isolate the fractions from 0 to 2 and then 2 to infinity. So very last step, alpha is 0 to 2. Alpha lambda between 0 and 2 is 0.1. So this is 0.1 lambda comma B at 2400 Kelvin by 0 to infinity plus 0.8 integral from 2 to infinity lambda comma B by the first one is a fraction at 2400 between 0 and 2. The second one is a fraction from 2 to infinity at 2400. So alpha is 0.1, f from 0 to 2, 2400, and 0.8, f from 2 to infinity at 2400. With your permission, I'm going to skip the details. This is the exact same thing as here, what we did, but it's at a different temperature, so your product of lambda and T is going to be different. It's 2 times 2400 or 4800 micrometer Kelvin. So calculate F 0 to 2 at 2 times 2400. alpha will end up being the following. The fraction is 0.6076. So this gives you 6076. F from 2 to infinity is 1 minus 0.6076. And so alpha becomes 0.37 something. So it's very much different from epsilon, 0.375. And epsilon was 0.702. Temperature of the surrounding is known to me. Ideal surface. T of the surface is 1200 Kelvin. It's a real surface because epsilon is not equal to 1. Then we calculate the net radiative flux for the object of the surface. I just want to introduce or reintroduce the term called radiosity because that's the next thing that I'm going to talk about today. But here is the idea. Q radiation. All of these are fluxes. The double prime indicating that they are a flux. This is by definition whatever is emitted minus whatever is the portion of the radiation that's absorbed. So this is E minus alpha times G. We have E, which is epsilon times EB for us. So in our situation, this is epsilon EB minus alpha G. I'll complete this and then define the radiosity term next. But G is nothing but irradiation from an ideal body, which is a 2400. So that's going to be sigma times T to the power 4 at 2400. So this is going to be epsilon sigma Ts to the power 4 minus alpha sigma T surrounding to the power 4. It is still not the same as what we looked at the beginning of the semester because this is not a diffuse and gray surface. So epsilon and alpha are different. And so this tells us that even if epsilon lambda is equal to alpha lambda, it's not necessary that epsilon and alpha be the same. As you can very well see, they are vastly different from each other. We'll calculate these. So Q double prime radiation is 0.702 times sigma, which is 5.67 10 to the power minus 8 watts per meter square Kelvin to the power 4. And this is Ts is 1200 to the power 4 minus 0.375, 5.67 10 to the power minus 8, 2400 to the power 4. Substitute and calculate. This will give you a negative value. It will end up being minus 623. Which implies that the net radiative flux is into the surface. It's not away from the surface. So the surface is getting more energy from the surroundings than it is giving off, which tells you that if this were a transient problem, transient conduction if you will, the surface or the object will keep getting hotter as time goes on because it's receiving energy, it's not losing energy. Okay? And in the version of the problem that I'm going to post on Carbon, I have talked about that particular aspect of the problem, transient conduction, using these as initial conditions. So this is transient conduction under the guise of only radiative heat transfer. Okay? I don't want to spend time here because we've spoken about transient conduction in the past. Next step, I need to sketch the spectral emissive power for the surface or the object. So sketch E lambda versus lambda for the surface or the object. So first of all, I will sketch the spectral emissive power of an ideal body which is at the same temperature as the surface. Okay? This is E lambda. This is lambda in micrometers. E lambda is in watts per meter square micrometers. So that the area under this curve is going to be your spectral emissive power, which is going to be in watts per meter square. So for an ideal body, which is at the temperature of 1200 Kelvin, the curve looks somewhat of the following form. This follows the Planck distribution. Okay? So this is E lambda comma B at 1200 Kelvin for an ideal body. Keep in mind that the epsilon lambda versus lambda plot for us, I'm just going to sketch that very briefly here. This is lambda, epsilon lambda. This is 0.1, 0.8. This is the plot that we started off the problem with. It was given for alpha, but then it's a diffuse surface, so epsilon lambda is the same as alpha lambda. So it says that when I hit 2 micrometers, my spectral emissivity is higher. So which typically tells me that at 2 micrometers, if I sketch out the spectral emissive power of the actual body or the actual surface, that will also show a peak. But I don't know at what value of the frequency that this peak occurs. Okay, so there are 2 possible peaks for E lambda versus lambda. One of them could be at 2 micrometers because that's where the spectral emissivity increases. The other peak could be at this particular value, which I do not know what lambda that is, but I can figure it out. This is going to be lambda max. We can make use of Wien's displacement law to figure out lambda max. Okay, so I'm going to sketch that out here. I'll write this first. So for epsilon lambda versus lambda, first of all, lambda max times T is 2898 micrometer Kelvin. This is Wien's law of displacement. This is for the ideal curve. Okay, this is not for the real surface. So lambda max is 2898 divided by 1200, which is the temperature of the surface. If it were behaving as an ideal surface, this is approximately 2.4 micrometers. And so now there are 2 possibilities. Epsilon lambda for the surface, which is now a real surface, can be a peak at 2 micrometers, because that is where the plot tells me that, okay, the spectral emissivity has increased from 0.1 to 0.8, or it can be a peak at 2.415 micrometers, which is the peak value of the wavelength for the ideal surface. Does this make sense to everybody? I can answer any questions if you have. So this is now at 2.415. Here is 2. And so I'm not sure if I sketch epsilon lambda, which is going to be a carbon copy of this but scaled down by a certain value of epsilon lambda. But epsilon lambda comma b multiplied by this guy is obviously going to be epsilon lambda. I'm not sure if its peak is going to occur at 2 or at 2.415, and so we have to take recourse in those tables. So to figure it out, we need to calculate epsilon lambda at 2 micrometers and 2.415 micrometers. This has to be done from the tables. So it's kind of a no-brainer that the peak is going to occur at 2.415. Okay, because 2 micrometers is less than 2.415. But if I had given you a plot which said that, okay, and I'll answer your question in a second. If I had given you a plot that said that, okay, this range was not 0 to 2, but it was 0 to 3, then we would be in a soup. Okay? I would not really know whether the peak is at the value of lambda max or is it at the value of lambda where the emissivity is the maximum. Question.
Why is the point when it switches to the maximum when the maximum peak? Why wouldn't it get even bigger as we go along?
It cannot, it has to be lesser than what this guy is, isn't it?
Oh, by that law. Okay.
Right. It has to be lesser. This is for an ideal body. Whatever you're going to draw. So for example, okay, this is just an example. I don't know how the curve is going to look like, but if I were a thinking person, I would say the curve for the real surface, which is at 1200 Kelvin, is going to be similar to that curve, but maybe it's going to be something of this sort. I want to find out, okay, what is the exact nature of this curve, and I want to see if this peak is occurring at 2.415 or is it at 2. Okay? Yes.
Can you explain again why the peak could be at either of those two wavelengths and not just the
Okay.
calculated?
So from the figure that I've drawn here, this value is lambda max, which comes from Wien's law of displacement, and that is for this particular temperature 2.415. So it is possible that if I draw if this is E lambda, right? If I draw E lambda, then it is possible that this peak for E lambda could be at that wavelength. But I'm also seeing from the plot here that at 2 micrometers, my spectral emissivity is peaking up to 0.8. And so it is possible that perhaps the peak could be here. It could drop down and then it could go back down. I don't know. So we got to figure it out. We got to figure out, okay, is this the situation or is that the situation? And to do that, you have to calculate the actual spectral emissive power. Okay? All right. So how to do this? First things first, definition of E lambda. This is 0 to 2 pi, 0 to pi by 2, I of lambda comma E, sine theta, cos theta, d theta, d phi. This is the basic definition. But I know something about the surface. What do you know about the surface? The surface is diffuse, which means that this creature here is not a function of any of the angles, so I can just take it out and this becomes pi times I of lambda comma E, since surface is diffuse. And what I have to do now is figure out this value at those two wavelengths. And that's about it. Okay? So if I do that, then here is what I end up getting. So I lambda comma E at lambda is equal to 2 micrometers, 1200 Kelvin. If this were an ideal body, you would find out from the tables there is an entry, I think the third or the fourth column. I lambda comma B by sigma t to the power 5 is the column in your tables. So for the sigma times T of 2 micrometers times 1200 Kelvin, which is 2400 micrometer Kelvin, this value is the formula. So I lambda comma B, this is equal to 0.658866. Okay. Then likewise I do the same thing at the peak lambda. I lambda comma B by, and this is multiplied by 10 to the power minus 4, I'm sorry. I lambda comma B by sigma t to the power 5 for lambda times t is equal to 2898. This value is 0.722318. Times 10 to the power minus 4. So this is at lambda is equal to 2 micrometers. This is at 2.415 micrometers. And mind you, these are for an ideal body. This is not for a real surface. For the real surface, it's going to be a fraction of this. And so I lambda comma E by sigma t to the power 5 is going to be a fraction of whatever that you have there, and that fraction is going to be given by the value of the emissivity at 2 micrometers, which is 0.8 times this fraction. Okay, this is at lambda is equal to 2 micrometers. And since the spectral emissivity remains to be 0.8 beyond 2 micrometers, I of lambda comma E is still at lambda is equal to 2.415. Does this make sense to everybody? I just want to pause here. Here is what I'm doing. I'm calculating the spectral emissive power of the real surface, which I figured out is pi times this creature here. This spectral emissive power is 0.8 times the spectral emissive power of an ideal body at 2 micrometers and beyond. So all I have to do is calculate the intensity of the ideal body at these two wavelength values, 2 micrometers and 2.415, figure out which one is the larger of the two. Obviously this is going to be the larger of the two. And so I know that the peak occurs at 2.415, which is what I think any person would have thought at the beginning. But here is why I'm doing it, and I'll tell you in a minute. So this is the peak here. And if I draw the figure now, okay, this is the ideal body at 1200. This is lambda, E lambda. This is 2. 2.415. So starting from 0 all the way to 2, E lambda is going to be 0.1 times E lambda comma B. So that's going to be a small value. Okay. Right at 2 micrometers, if you remember looking at the plot of epsilon lambda versus lambda, there is a peak. This will then be pushed up there. But then thankfully I see that the peak for this creature occurs after 2 micrometers, which means that I'm still going to follow this curve now, which is going to be 0.8 times epsilon lambda comma b. So all the way here, this region is 0.1 times E lambda comma b. And then I see a peak, and all of this is 0.8 E lambda comma b, and then it just falls down. And so this is the distribution for the real surface. Does this figure make sense to everybody? And of course, why are we doing this? Is because the following situation could occur potentially. Supposing I have the following situation. This is lambda, epsilon lambda, 0.1 from 0 to 3, and 0.8 after that. How is the plot going to look like? This is E lambda comma b at 1200 Kelvin. So all the way from 0 to 2.15 is the peak here, or 2.415. Here is 3. Okay. Here is what the plot might look like. I don't know. You'll have to calculate the intensities and figure out if this is true or not, but the plot could look like this. You see, it will start